And welcome you to the 20th lecture of the STAR 2024 series. Topic of today's first lecture is Scientific Payloads for Solar System Exploration by Dr. Mehul Pandya, a senior scientist from Space Applications Center, Ahmedabad. And moderator of the lecture is Sri Asif Mohammed. He is currently working as a scientist at Space Science Division at Space Applications Center, Ahmedabad. He completed his BTech degree in physics, engineering physics, and MS in astronomy from Indian Institute of Space Science and Technology, Thiruvananthapuram. His primary research interests are gamma ray bursts, afterglows, and solar flares. Over to Sri Asif Mohammed.
Thank you, Dr. Praveen Kumar, for your kind introduction. So I'll be moderating this session. So any questions you have, you can type in the chat. We'll be taking that at the end of the lecture. So it's my pleasure to introduce Dr. Mehul Pandya, who is Group Director of Space Science and Environment Science Group in Space Applications Center, Ahmedabad. So Dr. Mehul Pandya started his academic career with BSc and MSc from Gujarat University and was a university topper for both the courses. He did his postgraduate diploma in atmospheric sciences from St. Joseph Fourier University, France, and did his PhD in physics. So he's an accomplished scientist with over 90 publications, which cover satellite remote sensing of biosphere, atmosphere, and space sciences. He has tremendously contributed to R&D activities within ISRO, with a major focus on optical polarimetry for aerosols for aerosol remote sensing on Earth and Mars, and for greenhouse gas detection with hyperfine spectral observation and theoretical modeling for same. He was also one of the team members for the Mangalyaan 1 science team. So with that, I invite Dr. Mehul Pandya to give his talk on the instruments for the solar system exploration. Over to you, sir.
Okay. Thank you, Asif. Thank you for a nice introduction. And good afternoon to all the participants who have joined this online session from across country. And good afternoon to all the organizers, especially Dr. Praveen Kumar from the Space Science Office and IIRS organizers. Hope I am audible and my presentation is visible to you. Is it? Yeah.
Yes, it is visible. It is visible.
Yeah. So in today's brief talk, in this lecture, we'll try to discuss various aspects of scientific payloads for space exploration, not only the solar system exploration, but space exploration at large. And we will have two kind of discussions: why solar system exploration studies are being done and how it is being carried out using scientific payloads. And particularly we'll discuss with photographs and videos the details and development of scientific payloads used for space exploration studies. And as we know, space exploration is the use of knowledge of planetary science, astronomy, physics, and especially the cutting edge space technology to explore the outer space. So we'll begin our discussion with what are the scientific payloads. Basically, they are the instruments designed to collect the data from remote platform for scientific experiments in order to increase or enhance our understanding about universe and solar systems. The basic primary benefit of these payloads are the payloads which are put on the spacecraft can go to the very far distance, which allow us to collect data and perform experiments in very harsh and challenging environments that are otherwise inaccessible to humans. There are various kind of payloads one can think of. The main one are scientific payloads, which are people do observations through these instruments. Communication payloads, which are used for far distance communication, data exchange, navigation to navigate the spacecraft and instruments. Human support payloads, that means they are used, human support payloads and cargo payloads, they are being used for manned mission for life support, the keeping environment quite safe, and various kind of spare parts of spare parts which are being taken to the space station and those kind of missions. But today's discussion we'll be discussing about scientific payloads. Basically, development of such kind of technology or instrument started with the first launch of satellite Sputnik in 1957. Now it has been more than 6 decades. These technology and scientific understanding has advanced to quite a greater height. However, this process of designing space payloads or instruments, they look quite exciting, but they are very, very challenging and difficult because they have to work in very, very extreme and harsh conditions without direct intervention from humans. And these kind of instruments, they go through several stages of development, starting with a paper design or functional design to an instrument with various testing with proven performances, and which ultimately flies on the final finished mission. So there are various stages. We'll try to discuss with example what are those. Very major stages of development of any space science instrument are, if you can see the right hand side photographs, where we develop these scientific detailed specific instruments. They are being designed by various institutions. One of that institutions, premium institutions, is our Space Application Center SAC, Ahmedabad, which is a premium lab of ISRO, which is indulged in such kind of scientific instrument development for Earth observation, planetary sciences, or space exploration studies. So various institutions around the world, they develop these instruments and they deliver it to the spacecraft for its integration into spacecraft. The second stage, you could just see, these are not the exact stage, these are very rough major steps I am showing. These scientific instruments, they are then being integrated inside this kind of satellite bus, and with this satellite system itself, various tests they are undergo with all the subsystems, because they have to see the performance of various commands, telemetry, power, thermal and mechanical properties with their extreme limits also. So once this satellite is ready, they are being transported to the, let us say, for example, here in India, we transport it to Sriharikota, our launch pad of India, and they are being integrated into the rocket system. And they are then being, on the specific date and time, they are being launched through our GSLV or PSLV vehicle. Once after the launch, the scientists or engineers who have developed or designed these instruments, they are the main persons who have developed that instrument. They know how to operate it within flight through various commands and various modes. They operate through our telecommand and control station, and they try to observe that particular instrument for specific scientific purposes. So these are the major stages through which this instrument goes through. The major themes where these kind of instruments are being discussed generally are, one can say, planetary sciences, astronomy and cosmology, and heliophysics kind of themes, where we understand the astronomy, cosmology are study of objects or processes or of phenomena in space, And cosmology is the study of origin of universe and its evolution. And we observe it through various instruments. We'll see some of those examples. Planetary science, those studies, they include the study of various planets, including our own Mother Earth, and celestial bodies, moons, asteroids, comets, etc., and planetary as a system. Planetary systems as a system of systems we study within planetary science. And heliophysics, which is nothing but a comprehensive study of sun, solar system connection, understanding of Earth space environment, or various phenomena in space which is influenced by various star like sun. So that's why people say it is a combination of, let us say, heliosphere, which is solar physics, space weather studies. So people use various scientific instrumentation for this kind of scientific exploration study. But what do we observe in university? We would like to make instrument, but what do we observe? So these are very major components, major, important elements which we generally would like to observe. First one is electromagnetic radiation through, remote sensing, method. Without touching or without going into those, about object from far distance, we try to understand the properties of certain object through photometry, spectroscopy, or polarimetry, where we try to understand the radiance or radiation from the object, what is its spatial distribution, how that radiation is distributed as a function of wavelength or frequency, and what kind of scattering and absorption properties are being observed through some of the polarimetric observations. Second category are particles, which are somewhat, one can say, in situ. Within that medium, one can observe various particles, either it is nuclei, cosmic rays, electrons, protons, and neutrons, because they emerge from various processes, and one has to observe this kind of particles. And very peculiar kind of waves, gravitational waves, considering the fluctuation space and time. So we'll one by one we'll try to see how we observe and with which instruments we observe electromagnetic radiation, particles, and gravitational waves in subsequent slides. So we'll start with the electromagnetic radiation. That electromagnetic radiation, which is, one can think of having various wavelengths or frequencies, starting from radio waves to very high frequency X-rays and gamma rays, which is covering from very low to high energy levels also, which are prevailing in solar system. And one can observe this kind of electromagnetic radiation with various probes. And we all know electromagnetic waves, they are radiated from a form of a wave resulting from the motion of electric charge and magnetic field, which are perpendicular to each other, and they are the main primary mode of observing the very far distant universe. And as we discussed, it can be observed through imaging, spectroscopy, and polarimetry. So how one can observe this? We'll try to see imaging, spectroscopy, and polarimetry. As the name suggests, first imaging is to image certain objects or media, how much the light is being spatially distributed, how they are being actually propagated in various mediums. And once we observe through cameras or spectrographs or spectrometers, one can have this kind of observation. Just simple examples of some images, beautiful images of Hubble and James Webb are shown, which are being actually observed through imaging and photometry. After imaging that, we observe these kind of objects at different wavelengths. Why different wavelengths are important? Because the wavelength which is having different kind of frequencies and the wavelength numbers, they infer information about various phenomena occurring at different energies and different levels. And if we observe, like what you see on right hand side, the sun is observed at various wavelengths of very high, very means moderate wavelength to very low wavelength of 130s, 90s angstrom to certain 1700, 1800 angstrom, and you could see how these information of various levels or various media of sun, its surface, its corona, they are being manifested as a function of wavelengths. So this is the beauty of multi-wavelength observations, and if you do it through certain vantage point, it can give you very detailed observation of some of the processes, some of the objects which otherwise would have not been possible. Or these are multi-wavelength observations where the universe, we know universe presents a wide range of extreme environments from very cold to very hot background, which can be probed from radio to gamma ray spectral regimes. And basically it provides you the different and unique information about varied properties of the target and the medium. This is a same sample of space which is being sampled at various frequency levels or various frequencies, which is around radio frequencies to gamma rays, which actually bring out detail of various levels on various information about this particular sample. Obviously the spectroscopy, which gives you how radiation from any object is being distributed across frequencies, because depending upon the rotational, vibrational processes which are being occurred, which occur at various spectroscopic level, it can give you a unique information about emission processes, chemical composition, temperature of certain targets, and which generally gives continuum or line emissions. We are not going into great details, but the fundamentals, one of the spectral distribution laws or two laws which are very, very important, we'll try to see simple law. One is called Planck's law and another is called Wien's displacement law. They are very, very important as far as remote sensing of any object is concerned. This we can just briefly discuss. Planck law describes the spectral distribution of electromagnetic radiation emitted by black body at temperature T, which is nothing but 2 pi hc square upon lambda raised to 5, 1 upon e raised to hc upon lambda kt minus 1. And you put a temperature, let us say 300 Kelvin, and then change the wavelength at lambda, you would get a distribution of radiation, and which can be seen for varying temperature, how envelope of spectral radiance are charted out. This pink color provides you spectral distribution of 300 Kelvin object, black body object, and then 500, 750, 1000, 3000 and 6000, which is somewhere around. So if we see the temperature of Earth, by and large, if we consider it to be approximately 300 Kelvin, the Earth by and large emits its radiation somewhere around this particular envelope, with the peak emission somewhere around 9.6, 9.7, 9.8 micrometer. So if one has to do thermal remote sensing of Earth, he has to do remote sensing somewhere around 9.8. But if I wish to see sun from remote sensing platform easily, it has its peak somewhere around 0.5 micrometer. So for 300 Kelvin, it is 9.8. At this particular 6000 Kelvin, it is somewhere around 0.5 micron. And as a function of temperature, the peak shifts systematically towards lower wavelength as temperature increases. And this translation of peak is manifested as Wien's displacement law, which is shown here. So one can use these laws to understand what kind of observation we have to observe at which temperature and which wavelength. And I have to, if I would like to observe a planetary body of 600 Kelvin, I should design my instrument with a certain characteristics. If a temperature is quite high, I have to design according to that particular thing. So for example, if I need to observe Earth, which has a temperature somewhere around 300 Kelvin, we obviously have a window around 10 micron. Mars, which has a temperature range of 130, 140 Kelvin to 280 to 90, it has to be done at specific temperature, specific wavelength region of higher, somewhere around 13, 14 micrometer. And if we talk about Venus, which has quite a large temperature range, it has to be observed by considering these temperature distribution. So these are the consideration. If we understand the basic physics, you have to consider it for the design of any scientific instrument. The beautiful example of black body radiation law was actually exploited by these two gentlemen, Dr. Smoot and Dr. John Mather, who have designed an instrument called FIRAS on an instrument, space-based instrument, COBE, Cosmic Microwave Background Experiment. And they measured the CMBR, the residue, humming of the so-called initial days of universe. And there they actually, what they did was they understood the black body radiation distribution of temperature equivalent to 3 Kelvin, which is nothing but somewhere around millimeter scale. And they designed their instrument in this particular wavelength region, and they could detect the CMBR, which is very, very, feeble signal in the universe. And they actually received the first of its kind, Nobel Prize in physics using satellite-based observation. So if we understand the spectral distribution, design scientific instrument, it can fetch Nobel Prize as well. That is the point to be noted. One of the beautiful instruments in the history of remote sensing or space, exploration studies is Hubble telescope, which had various cameras, spectrographs, and interferometers, which observed universe at a or various, they sent beamed beautiful image of various, images of space, which has revolutionized the understanding about the universe. And one of the examples, if you just see the spectrographs, because spectrographs, breaks down various lines, they break down their components and how generally prism splits the white light into rainbow. And by these characteristics, it can give you the understanding about temperature, density, chemical composition, and various observation. Here, I'm showing a space telescope imaging spectrograph, STIS, which has observed a massive star pair, and they could show the presence of helium, argon, iron, nickel kind of species, and which gives you an important clue about the processes which are going on in some of these kind of objects. The next one was or is beautiful, one of the unique kind of telescopes, that is James Webb Space Telescope. Most of you are aware of these. They actually have a primary mirror which consists of 18 hexagonal mirror segments, and which gives you a 6.5 diameter equivalent mirror, which is compared 2.5 to 3 times of Hubble telescope. And it gives you detailed, very high spatial resolution and beautiful observation through middle infrared, near infrared observation through spectrometer, camera, and spectrograph, and which gives you finer details compared to any other space telescopes which had given earlier observations. This is the example of one of very beautiful image of black hole, which was observed, supermassive black hole observed at the center of galaxy M87, because around 100 years back, black hole was just an equation. And somewhere around, last 20 years or so, and especially in 2019, the first ever picture of this closest supermassive black hole at the center of galaxy M87 was imaged through processing of thousands of image, which is, around 26,000 light years away, which was captured through Event Horizon Telescope. And you could see the emission from hot gas swirling around the influence of very, very strong gravity near the event horizon. And these kind of observation, they are being observed through a technique called very long baseline interferometer, which is called VLMI, and which gives you almost virtually Earth-sized dish, which provides you very detailed resolution by putting these instruments at various geographical location. You could see left-hand side of small, view graph, and this kind of unique observations were made. After spectroscopic and that observation, the very detailed, important hidden information one can get it is through polarimetry, which is basically the measure of polarization of the light, which can give you information basically about this scattering. Typically, scattering induces the polarization, or many times emission mechanisms that also cause polarization, and this gives you some hidden information which otherwise would have not been observed through the intensity measurement. This example of polarimetric, X-ray polarimetric observation, where you could see the large image of IXP combined with Chandra telescope observation in blue and optical light in golden color with Hubble, which basically observe a supernova remnant. And these lines, which are basically graphical lines which come from IXP polarization measurement, which researchers say they show the direction of magnetic field across the regions of this remnant, which provides you very some of the secret information through polarization as well. The last part is through observation of particles. So solar winds and particles within solar system. Generally, solar wind is a stream of what we understand, stream of charged particles released from upper atmosphere of sun, and which is called corona, and consists of electrons, protons, alpha particles. So those kind of ions and those kind of particles are being also emitted, are being also thrown out of various systems, which have to be also observed. And that direct detection of these kind of particles are possible through which can give you understanding about solar winds the corona mass ejections, CMEs or atmospheric processes, and which can give you information through instruments called mass spectrometer. The mass spectrometer, what does it do? They detect the particles created by various processes, as we discussed, and it converts molecules into ions, and under the influence of electric field and magnetic field, these ions are manipulated in presence of these fields, and they are being basically based upon their mass to charge ratio, they are being separated, and understanding about the mass, charge, temperature, velocity distribution can be observed about the particles. The another important field which people do is gravitational waves, which are the ripples in space time, which are caused by some of the most violent and energetic processes in the universe. And as Albert Einstein predicted, I think in 1920s, that in his general theory of relativity, where his mathematics showed that some of massive and accelerating objects like black hole and neutron stars orbiting each other would generally disrupt the space-time in such a way that this kind of waves they undulate the space-time and propagate in all direction away from the sources. So what these are some of the latest frontiers in astronomy, where people observe mergers of very big and heavy objects, and which provides the ripples in space-time. And some interferometric, high sensitive interferometric instruments are being used for observing this kind of phenomena. And researchers have planned a instrument called LISA, laser interferometer space antenna, as a combination of 3 systematically revolving satellite, which would provide interferometric long baseline and interferometric measurement to observe the gravitational waves. So now, within last 5-7 minutes, I will try to show you some of the examples of remote sensing instruments, how they are being designed, and what kind of observations, scientific observations they show you. And they are working at various wavelengths. First and foremost is our own Mars color camera on Mangalyaan 1, which was basically RGB camera. You could just see the size, mass, and power of this instrument. So whatever space instruments are to be designed, it has got great constraint of only small size, very small weight, and very small power, and which provided beautiful images of Mars. I will show you. This is a first and last image before leaving for the Martian, transient orbit on Earth orbit. MCC took this Earth image. This is the first Mars image on 24th of September 2014, the first image of Mars, which was taken by this camera. This is a global various pictures in 2014 MCC camera has taken. This is one of unique pictures of Valles Marineris, one of the largest canyon system of 4,000 kilometer in length and 2,000 kilometer wide and 7 kilometer deep, which gives you a various idea of various clouds. They are being actually seen in this image, or Martian clouds as seen in Arsia Mons. So sitting at Earth, sitting at Bangalore, at our deep space network, this kind of information you get on your desktop through some of the scientific instruments which were designed. Then optical and infrared imaging spectrometer, like MOM thermal infrared imaging spectrometer, which worked in thermal regime, or JWST, as we discussed, one of the spectrometer which works in middle infrared, wavelength range of 5 to 28.5 micrometer region, which gives unique observations. Hubble also had this kind of information. Or X-ray imagers, where they are quite, sensitive to solar flares and gamma ray burst, phenomena. So these are the instruments which were there on AstroSat, SXT, or some example of NASA. I don't want to go into detail. This is just for your information that as a function of various wavelengths, one has to design these kind of scientific payloads or instruments, keeping in the mind the wavelength regions, how to observe it, what kind of unique observation it would provide. Then X-ray spectrometer, which gives you elemental abundance or composition of plasma, which is very, very important for understanding the supernova composition or solar flare composition. So Aditya L1 has these Solexes and Heliois, soft and hard X-ray instrumentation, or NASA and JAXA had various instrumentation. Some of them are shown here. UV imaging and spectrometer, which provides very chromospheric and coronal information about sun surface. So AstroSat, we had UVIT, and one of very unique instrument of NASA, Cassini. There are many instruments. These are two of these instruments I'm showing. UVIS, which gave us spectacular information about very planetary environment. And obviously over Hubble and other instrumentation, this kind of spectrometers are also situated or sent. Coronagraphs, which are nothing but optical devices which are used to study very, very faint, regions surrounding very bright stars or sun, so that you could understand very detail about some of those processes. Aditya L1 had VLC or has VLC, visible emission line coronagraph, or SOHO also had, NASA's SOHO also had this kind of observations. I will show you few in situ observations, how it has to be done. It has been done by some instrumentation. One is magnetometer, which measures the direction, strength, and variation in magnetic field to provide the detail of magnetic field around Earth, Sun, and other planets. Aditya L1 has its own magnetometer, and earlier Voyager and various instrumentation or space probes had this kind of in situ measurements, magnetometers. Langmuir probe, which is one of the very famous or very popular instruments, which measures the electron density, electron temperature of plasma, plasma potential, electron energy, and distribution of these kind of species, which provides you understanding about the Earth ionosphere and environment of other planets also. In future, we will have also, ISRO will have a instrument on Disha, where we have a high frequency Langmuir probe, and Disha will be a future instruments, pair of instruments will be sent. And MOVAN and other NASA's mission also had a lot of instruments at this Langmuir probe. As I said, it is a popular one. Retarding potential analyzer, RPA, which are particle analyzers, which basically observes the charged particles through various engineering, and the Aditya L1 and other instrumentation also had this kind of instruments. Mass spectrometers, as we discussed, it's also very popular, very important instruments which measures the mass to charge ratio of neutral particles to use to understand various materials, including gases, liquids, and solids, and various space probes had. MOM also had instruments called, very popular instrument called MANCA from ISRO, and there are various instrumentation on MOVAN, Venus Express, which also had this mass spectrometers. The last section, just 2 minutes, I would like to just show you various components. Generally, people have to, or researcher have to understand in designing a space instrumentation. I will take electro-optical instrument as an example, where you need to have observation of radiation through certain celestial objects, collect it through optics, and then detect it and read it through electronic systems, where you obviously have to have electro-optical imaging instrumentation, which will have focusing optics for light collection, dispersion system, detection system, electronics, and mechanical assemblies. So, and for space-based probes, you need to have low weight instrumentation with low mass, very good thermal stability, very good optomechanical sensitivity with less coefficient of thermal expansion or moisture expansion, should be very, very lightweight, which would work. This material would work in very harsh environment also. And it can use refractive, reflective, or some, catadioptic kind of instrumentation for which can cater from very large optics to very, small optics having less temperature, less weight and mass. And the last one, but not the least, is the detector system. There are various kind of detector system. As a function of wavelengths, one can observe through silicon photodiode or in various kind of, infrared observations, and, thermistor bolometer, MCTs, and various kind of, pyroelectric instrumentation. So, in summary, I would again come back to the major, to just summarize the total talk. One has to develop specific instrument depending upon the problem and scientific object to be observed. It has to be integrated, it has to be launched, it has to be monitored, it has to be ultimately operated through your specific plan with a very, very precise management and planning, which would ultimately give you improved scientific understanding about celestial objects and universe, which pave the way for the discoveries. So this is my last slide, where, people say that one can easily make instrument, but the difference between simple instrument, which is an affordable and scientific sound instrument, sound mission, with not a great mission, is the difference between development of cutting edge technologies. That means recent advanced instrumentation development and basic physics, engineering, discoveries of materials, and those go into development of scientific instrument, and that gives a great, way for developing beautiful scientific instruments. So I thank you. I acknowledge Chairman ISRO, Director SAC, Director SPO, Dr. Praveen Kumar from SPO IIRS team, and obviously all the participants who are joining this particular, who have joined this session, and my team members here at SAC, specifically Asif and Manish, for all the help. Thank you. And I stop here. Thank you. Thank you very much.
So thank you, Dr. Mehul Pandya, for the wonderful lecture and overview of various payloads and instruments that has been flown, and general principles for designing a fruitful space observation payloads. Now let's see how the let's go into some of the questions asked by the yeah, so let's go into some of the questions asked by the students. So one question is, can we observe gravity waves? But I believe that what he meant is gravitational waves, because gravity waves have different phenomena. So I think question. Can we observe gravity waves, which I believe he meant gravitational waves? That can be answered now.
Yeah. So I think student is asking about the observation of gravitational waves, I suppose. So obviously, as we discuss, it can be observed through some of the techniques as we discussed with very high precise interferometric observation with fine electromagnetic radiation measurement, and one of the important examples is LIGO experiment, which is operational, and one can observe these gravity waves through LIGO experiments. And as I discussed, some of the experiments, space-based experiments, people are proposing or people are discussing through making very long baseline by using space-based instrumentation, LISA, as I discussed earlier, it can be observed. So there are a lot of experiments, lot of measurements, lot of efforts are going on, and one of the examples is LIGO, and Indian LIGO experiment is also being discussed, being planned at various forums.
Okay, so thank you for answering question. Another question is, how can you transfer the information from distant planets to Earth? So it's basically regarding the communication requirements, the bandwidth, other constraints for a space exploration.
Yeah, it's a good question. As we discussed, development of instruments or development of spacecraft based payloads is challenging, but the more challenging is to some of the constraint, as we discussed, constraint because of mass, weight, and the volume. And another important constraint is with respect to the data which can be stored on board and which can be transferred to the ground or to the earth. For example, as far as Mars mission is concerned, we had to go for, let us say, 5 to 6 crores kilometers, and after traveling to that much of distance, we had to have a direct communication from space-based instrumentation on board MOM to our ground-based 32-meter antenna at Bailalu Indian Deep Space Network. But the instrumentation had a very less space for recording, because these MOM mission had to be lightweight, and you could not you could not afford very big disk on board. So less amount of data could be observed, and that had to be transferred to the ground station. So while designing the instrument, engineers and scientists, they have to consider what kind of bits per seconds and total, let us say, certain gigabytes of the data rate has to be there are constraints, and those constraints have to be considered, and that can be transferred to ground-based antenna, ground-based station with very careful calculation and considering all the resources. So those constraints have to be considered while designing any space-based instrumentation. Thank you.
We'll take 2 more questions. So second last question we'll take is, Harshvardhan has asked, how can spectroscopic analysis help to identify if the composition is pure or a mixture? So I guess you can explain how
pure or mixture. Okay. Regarding spectroscopy. Okay. as the term said, spectroscopic observations provide you the observation of about any object or medium as a function of wavelengths. And the once you have a spectral distribution of radiance or energy as a function of wavelengths, you understand the basic absorption features of specific, target specific features of mineral, specific features of species. We know the basic observational. Let us say, for example, if I want to go for a observation of oxygen or carbon dioxide, so I have concentrated on a wavelength somewhere around 2 micron, and if it has a pure carbon dioxide only environment, it is easy to observe. But we may have carbon dioxide mixed with the water vapor in the atmosphere of any planet, either it is on Earth or it is on probably on Mars or some other planets. So you have a mix of these spectra. Depending upon the understanding of basic absorption features, spectroscopic modeling, radiative transfer simulations, which comes with the understanding of basic rotational, vibrational, spectroscopic information, we understand what kind of, features would be manifested in those spectra, and we decouple depending upon the basic understanding of, let us say, 2 species, and one can easily separate out depending upon understanding of basic physics, basic spectroscopic, and basic mathematical modeling scheme. So people decouple, people separate out this kind of observations and spectroscopic details out of combined spectra. Yeah, and there are other methods of decoupling this: spectral mixing, unmixing, and those kind of basic methods are also available where one can separate out this kind of features. Yeah, thank you.
Yeah. So another question from Daja R is, what are the payloads in lunar exploration? So I guess
lunar exploration,
Chandrayaan is probably
okay.
What is?
Yeah, I think so. I am not expert on that, but most of the I can just list out. We have had Chandrayaan 1, Chandrayaan 2, and recently Chandrayaan 3 missions. Chandrayaan 1 hosted various instrumentation from India and various, global laboratories. The main instrumentation over Chandrayaan were camera, then terrain mapping camera, which could give you 3D composition or 3D structure of the surface. Then we had spectrometer called M-Cube from NASA, which worked somewhere around 0.4 micrometer to around 3 micrometer or 2.5 micrometer, which was used to discover the presence of water molecules on the lunar surface, and which was the discovery from the Chandrayaan 1 mission. Chandrayaan 2 also had orbiter and other module of lander rover. But orbiter actually worked very well, which also had spectrometer, which worked, which is called IIRS, which worked from, I think, 0.5 micron to 5 micron, which also covered the full spectrum of wavelength, and which unambiguously observe the presence of water molecules somewhere around 3 micrometer. It also have a very beautiful instrumentation called the synthetic aperture radar, DF-SAR, differential SAR, which also gave a very good observation about subsurface characteristics, subsurface, ice and other characteristics, which work in actually microwave region. Then Chandrayaan 3, it also had the terrain mapping camera. Then Chandrayaan 3 all had various instrumentation, especially on lander rover. If I remember rightly, it has a chest over its, for temperature and thermophysical instrumentation. It had libs on rover, that is called laser induced breakdown spectroscopy observation. It had navigational cameras. It had very detailed observational instrumentation. It had a seismometer, instrumentation. So I think Dr. Praveen is also there. He can give list of Chandrayaan, instrumentation. But the main and important ones which I consider are, the important ones which actually discovered and which actually made a dent in the scientific community, which actually unambiguously said that Chandra or lunar surface has a water molecule present on the surface. So thank you. I think we can stop here. It is somewhere around 4:25, 4:30. So I would stop here. Thank you. Thank you very much.
Yeah, so let's all thank Dr. Mehul Pandya for this wonderful session, as well as answering all these questions. So over to you, Dr. Praveen.
Thank you, Sri Asif Mohammed, for nicely moderating this session. And also my sincere thanks to Dr. Mehul Pandya for a very well, informative lecture and throwing light on various scientific payloads on board of our Indian missions as well as international missions. Thank you, both of you, for supporting this program. Now we will move over to the next lecture, that is the 21st lecture of the STAR 2024 series, and today's second lecture, of course. And the topic is Telescopes for Solar System Studies by Professor Shashikiran Ganesh from PRL Ahmedabad. Shashikiran Ganesh is a familiar face to the participants, as he had provided the 10th lecture on minor bodies in the solar system. And the moderator of this lecture is Dr. Aravind. He is also familiar to the participants. He had moderated the session of Professor Shashikiran Ganesh also. So I know that there are many new participants in this session. So for the sake of them, some introduction is needed. So over to Dr. Aravind.
Arvind, you need to unmute.
Okay. So now we will hear the 21st lecture of the STAR 2024 series, and today's second lecture on telescopes for solar system studies by Professor Shashikiran Ganesh. Professor Shashikiran Ganesh is a very familiar face to our participants.
Good evening, everyone.
As he had delivered a lecture during this series on minor bodies in the solar system. And the moderator of this lecture is Dr. Aravind K, a postdoctoral fellow of Physical Research Laboratory. He is also familiar to you. He had moderated one session, the lecture on the same minor bodies in the solar system. So over to Dr. Aravind.
Hello, am I audible now?
Yes, go ahead.
Good evening, everyone. Sorry for the delay. Today, we have with us Professor Shashikiran Ganesh, a renowned faculty member at the Physical Research Laboratory. In a recent insightful speech, as Praveen sir has said, Professor Ganesh provided insights into the nature and dynamics of asteroids, comets, and meteors, shedding light on their origins and compositions. Today, we are fortunate to have him grace us with his experience once again as he embarks on a journey to explore the fascinating realm of telescopic observations. With his profound knowledge of telescope control and instrumentation, combined with his unparalleled enthusiasm for astronomy, Professor Ganesh is uniquely positioned to guide us through the intricacies of observational astronomy. His lecture promises to be an enlightening and enriching experience, offering us a glimpse into the wonders of cosmos and inspiring a new generation of astronomers. Please join me in extending a warm welcome to Professor Shashikiran Ganesh as we eagerly await the lecture on telescopes for solar system studies. Over to you, sir.
Okay. Thank you, Arvind, and thank you all to attend this lecture. I hope you can see the slides on the screen.
Yes, it is.
Yeah, okay, thank you. So in this talk, what I shall do is talk to you about telescopes of different types, and then also try and tell you how, what are the kind of telescopes that we particularly need for solar system objects, okay? And why we need, first of all, the telescopes, and what are the special things about, okay? So if you take a normal camera and put it on a stand outside in the night sky, and you take a long exposure image or a photograph with a long integration time of a few hours, this is the kind of pattern that you can see. You will see the trails of the stars in the night sky. So each of them is the track recorded by a star as the Earth rotates on its axis. Okay, with the pole star being sitting right here, just at about 1 degree away from the true North Pole. So this is what happens if you have the if you have a wide field camera sitting on a mount stationary on the surface of the Earth. So in the case of telescopes, we need to go the other direction. We need to rotate the telescope in the direction opposite to that of the Earth's rotation, so that we can track the object, celestial object, as it moves from east to west. Okay. So that's the typical thing. What I will do in this talk is I will try and give you some glimpses about what are the different types of telescopes, and also I will try and cover some of the points which in fact there's only one which really differentiates solar system observations versus the rest of astronomy. Okay, we'll come to that in the next few minutes. Typically, when you consider what kind of telescopes are there, we can subdivide them by wavelength. So starting from radio right up to X-rays and even gamma rays, we can observe using telescopes of different types. The only things that vary are the manner in which you collect the photons and the detectors that you use for sensing these wave bands. Okay, and you can also define them in terms of the light collecting element, whether it's a reflecting type of telescope or a refracting type of telescope. For example, at optical wavelengths, if you make the telescopes using lenses, which is what people used in the initial days, then they are called the refracting type or the refractor. Okay, and the largest is about 40 inch across, 40 inches of pure glass. The trouble with this kind of glass-based telescopes is that you cannot support a glass lens in the center. So gravity becomes the defining element in defining the shape of the glass surface of the lens. And it's not very easy to have a good quality image at the focal plane finally. On the other hand, with reflecting telescopes where you use mirrors, it is relatively easier to build larger and larger telescopes. For example, the largest currently operating ones are around 10 meter diameter, made of multiple segments. Okay, and the advantage there is that you can support them at the back of the mirror, and you can also define the shape of the mirror in an active manner. So you can compensate for variations in real time. Okay, I'll talk a little bit about that subsequently. These are telescopes where you make use of techniques called adaptive optics. Okay, so now let's look at what are the wavelengths of electromagnetic radiation that come from celestial bodies. Okay, so from the universe, from any of the objects in the universe, you can expect wavelengths of the electromagnetic spectrum right from radio, which comes to about a few thousand kilometers of wavelength, right down to gamma rays, where the wavelength is much smaller than an atom, 10 power minus 12 meter. Okay, and in this slide we have the details about the wavelength and then the typical scale of the objects that you can see at those scales. Okay, It also tells you what are the frequencies that would be associated with the corresponding wavelengths. And also, of course, as a black body spectrum, what is the kind of temperature where that particular wavelength would peak. Okay, for example, in visible light, the solar sunlight, for example, peaks at around yellow-green color, which is around 6,000 degree Kelvin. So this is typically the kind of electromagnetic spectrum that one can see from the stars and from other objects in the night sky or in the sky basically. And what you get from each waveband is something quite different compared to. So in order to have a holistic information about the entire universe, you need to study it at all possible wavelengths that you can have access to. Which brings me to the next question of how many of these are actually observable from the ground. Okay, so for example, this is, I think you might have already seen this by other speakers in this series, but just for the sake of completeness, let me go through it. Thankfully, the gamma rays, X-rays, and UV light are completely blocked by the upper atmosphere of the Earth, and thanks to the blanketing by the upper atmosphere, we are protected from these harmful radiations. What does get through to the bottom of the Earth surface is some amount of visible light, and there is a little bit of infrared up to about with small windows in in the near and mid infrared up to about 30 micron. Okay. Beyond that, again, it is completely absorbed, and you need to go to space in order to observe most of the infrared spectrum, including in the millimeter and sub-millimeter. There are few windows here. You can try and get some observations. It's not completely flat, completely absorbed at this point, but you do get some windows here, which allows some kind of telescopes, which I'll talk about in a moment, to observe these from high altitudes on the Earth's surface. Okay, so from something like 5,000 meters, you can have access to some of these windows. This is the plot as seen from the ground at sea level, okay, from the Earth's surface at sea level. Radio waves are essentially travel down to the surface of the Earth, and one can actually observe the universe in these bands relatively easily. However, even here, beyond a few tens of meters, the wavelength is completely blocked. Okay? So we don't have any major ways to observe the universe at longer wavelength frequency, or longer wavelengths than these. Now let me come to what kind of telescopes we have in the optical in this electromagnetic spectrum. We'll start with something which we should be really proud of, and that is the giant meter wave radio telescope, which is at these frequencies or at these meter wavelengths. It is the largest one in the world. Okay, it is near Pune, Kolad, near Pune in Maharashtra, and it consists of 30 dish antenna or a parabolic antenna of 45 meter diameter each. Okay, and you can judge the size of these mammoth dishes by looking at this small vehicle here in front of one of the antenna. So these parabolic antenna can be steered to any direction, and what happens is when the radiation comes down from the sky, it gets reflected from a series of wires which are essentially transparent at other frequencies, but at a wavelength of meter wave, they form almost smooth dish along the surface of this antenna, and they reflect the photons collected or the wavelengths to receivers which are sitting at the focal plane of this GMRT. Okay, and then the light is combined from there and fed through several kilometers of fibers and optics, fibers and channels, and one makes use of very complicated mathematical models to retrieve the images at radio wavelengths from this kind of a telescope. So this is one of the kind in the world, and India is now partner to a larger telescope which is being built in South Africa as well as in Australia jointly, and India will also be a partner of it. It's called the Square Kilometer Array, where we have interesting results expected in the future. Now, coming down in terms of wavelength to shorter wavelengths, we have the IRAM observatory, for example. I'm just picking and choosing just a few telescopes from around the world just to give you a flavor. There are many observatories and many antenna of this kind, except of course the GMRT, which is kind of almost unique, you might say. You have the IRAM observatory, which is a single dish of 30 meter size, and you can judge the scale of this thing by my figure standing here. Okay, so it's about 30 meter across in this dimension, and it is also fully steerable and can observe at millimeter wavelengths. So at millimeter wavelengths, what are the advantages is that you can observe a lot of large molecular transitions. Okay, so I think some of these things we covered during my previous talk, so we'll not go into it in more detail, but we can have questions if people are interested. The other development which has happened in recent times, IRAM is an old telescope, but in recent times we have had the another telescope called the Atacama Large Millimeter Array. Okay, so this instrument works from about 0.32 micron, 0.32 millimeter to about 3 millimeter. Okay, and it has 66 dish antennae of various sizes. It's essentially a 12 meter kind of antenna, dish antenna, and 66 of them laid across the plateau of Atacama in Chile in South America. It's it's at an altitude of 5,000 meters above sea level, and it's almost next to impossible to work there in real time. So one is not allowed to stay there at the top of the plateau for very long duration. All of the work is done remotely, of course, and we have a computer control to receive the data from this kind of a dish. So the light is again reflected back from here into the receiver, which is sitting at the top, and the receiver would have different kind of sensors, bolometric cameras and bolometric arrays, which allow you to retrieve images of the night sky in the millimeter, sub-millimeter wavelengths. Again, this has a very important role in terms of molecular emission detection, and nearly 140 molecules of various complexities have been seen in the interstellar medium and in various objects of the universe, and this ALMA is to be thanked for that. Let's now look at what is the advantage of going to space for the other kind of telescopes. Essentially, of course, the first point is that you have access to wavelengths that don't reach the ground. And the second is that, for example, at optical wavelengths, the moment you go outside the Earth's atmosphere, you are outside of the effects of the Earth's atmosphere. For example, the night sky, if you go out on a typical night in the middle of a city, you will find that it is there's a lot of twinkling happening in the night sky. Okay, the stars appear to twinkle. But the moment you go to higher and higher altitudes, the amount of atmosphere goes down, and then the sky starts becoming more and more stable. And the moment you go into space, there is no turbulence at all near the telescope. So you essentially end up having a wonderful diffraction limited image from the instrument. So what are the telescopes and observatories which are working in this direction? I will highlight only a couple of telescopes of recent times, but not the very newest JWST. One reason being that it is interesting to see what kind of science was possible with these bands, which, for example, the Herschel Space Observatory. This was a telescope of 3.5 meter size, this part here, and it's completely shielded from one direction, and then you can point to any part of the sky. And it was made essentially for far infrared and sub-millimeter observations. All of the entire telescope was cooled using liquid helium, and also the suite of instruments, which were essentially photometers and spectrometers and imagers, of course, working in at the focal plane of this 3.5 meter dish, where the light was guided from the primary to the secondary and through a hole in the primary into the later part where you have the cryogenic tank and all the suite of instruments there. So fantastic set of results from this observatory for all kinds of objects. And in case of solar system science, it was the peak was to get information on the sizes and albedos of minor bodies in the solar system. So this was an important mission in that sense. Other missions of this kind which have been very useful are the WISE and NEOWISE missions. And I hope that those of you who are interested will go and look at those missions also separately. Coming down in wavelength to more closer to optical, this one is the Spitzer Space Observatory. You can get a glimpse of the size by looking at this technician working on the solar panel of this observatory prior to launch. This was also a cryo-cooled observatory with a large mirror and cooled imagers, spectrographs, and so this is the instrument which made a lot of images of the night sky at near to mid-infrared wavelengths, and there's some fantastic images if you go and look up the glimpse survey of the Milky Way, for example. Okay. There have been, of course, some measurements and spectra of, in the mid-infrared using this observatory for comets as well. And they found that there is a large similarity between the cometary spectra and the spectra of young stellar objects. In fact, the first of those results was from the Infrared Space Observatory, which was launched by the European Space Agency. Okay, and so they were the ones who first showed that the comets had material which were very similar to what we see in young stellar systems today, where stars are just forming. So that gives you further direct proof that studying the comets is like studying the young stars that are being created. Okay, so it's a record of the history of our solar system as well. So that brings me down back to the Hubble Space Telescope, which is of course quite famous. I think all of you would have heard about it. This is still very active and still providing us with a lot of very exciting results. I'll just show you two images which show you why going out of the Earth's atmosphere has made a fantastic contribution. This telescope has detectors and instruments working in the optical and UV, as well as in the infrared, and they had several generations of instruments through the possibility of changeovers by the astronauts on the space shuttle. So a couple of examples from this observatory are the color mosaic of Saturn here and Jupiter on the right. Saturn's polar aurorae are seen in this false color composite, where the STIS UV images and data were combined with the ACS visible light to show you the auroral emissions in the Saturn's polar regions. Okay, and similarly, this is a very high resolution imaging of Jupiter's surface immediately after the comet Shoemaker-Levy 9 had impacted. Okay, there were 20 fragments which hit Jupiter one by one, and although they were all hitting Jupiter on the other side of the Jupiter when they hit the comet, hit the planet, but when the field rotated into the field of view of Earth, that is when these images were recorded. Okay, so they are several hours after the first impact, and but still you can see very well how this developed further. So as I said, you can launch telescopes to space, But at optical wavelengths, you want to avoid turbulence. That's why you want to send them to space. Okay, but you can also do the other way. You can study the Earth's atmosphere and how it is varying over a short period of time, and build optics in such a way. It's called adaptive optics, such that you can compensate for the turbulence in the Earth's atmosphere in almost near real time. Okay, and by doing that, you can go for larger and larger telescopes. Why do you want to go for larger and larger telescopes? Simply because larger telescopes means better resolution, and you can also get more photons, which means that you can have much better instruments and much more high signal to noise ratio measurements of spectra or images or whatever you are wanting to observe. So this is one of the techniques, the adaptive optics and active optics, which allows you to compensate for the Earth's atmospheric turbulence, what we call seeing in technical terms, and as twinkling in the layperson's language. So examples of such telescopes are many. And I just show you one example here. This is the European Southern Observatory's very large telescope, an array of 4 8-meter class telescopes, which are sitting here. And they also have smaller telescopes sitting along with them. And this is a close-up view of that. Light from all these 4 are combined subsequently in order to get interferometry. But you can also individually observe each telescope can observe individually different targets, and you can use them as a conventional telescope also. The latest observatory which people are planning and building right now, and which will be coming online in the next 1 or 2 years, is the Vera Rubin Observatory, also called earlier the LSST, Large Synodic Survey Telescope. This is a fantastic piece of instrumentation, and it is coming up again in the desert of Chile, not very far from the VLT and Alma site. And it is based in the desert, of course, and at high altitude. And the design is quite interesting. It is having 3 mirrors. Okay, you have the outermost mirror. So this is the parcel of light, primary mirror M1, which is 8.4 meters across. Okay, and this light then gets reflected to the second mirror here, which is called M2, and this is a mirror which is 3.4 meters across. Okay, and from there the light gets further reflected to the central part of the M1, which has a different kind of shape, okay, a different configuration. And so this is one piece of glass, but 2 different shapes on the same surface. And then from there, it goes through a series of corrector plates, which are shown here, and falls on a camera, which is the largest ever made camera in India, in the world. It's the camera itself is 64 centimeters across. Okay, so the detector plane is 64 centimeters across. The filters in front of it, which decide what wavelength you are observing at, is 76 centimeters across, and that's bigger than some of the other bigger refractors which were made. And then you also have a corrector plate L2 and then an L1. And the L1 corrector plate is 1.55 meters, which is almost as tall as a human being, right? So that's the largest ever lens built for astronomy or for any other purpose on ground. So all of this provides you with diffraction limited, not exactly diffraction limited, but seeing limited images right down to 1.75 degrees from the center of the field of view. So you have a 3.5 degree diameter field of view of this with this telescope. So at a time you can image 3.5 degrees of the sky. So what does that tell you in terms of science? It means that it's going to be able to survey all kinds of objects which vary, and you are going to be able to cover the entire night sky within 2 or 3 nights. Okay, and which means that on any given night you should be able to track more than 5,000 asteroids or near Earth objects or trans-Neptunian objects or comets or whatever you like, okay, which show their presence by moving across the field of view as a trail. So this is going to really revolutionize our understanding by really extending by manifold the catalog of solar system objects. And we're looking forward to getting the results from these from this observatory to follow up and study all the new objects it's going to find in the very near future. We expect it to become online, I think, in the next couple of months to a year or so. Now let us look at some of the Indian optical and infrared observatories. It's not a complete listing by any means. I just picked and chose some examples just as a flavor of what is going on in the country. And let me start with what used to be the largest telescope built in India. And I guess built in India, it's still the largest. It's the 2.34 meter VBT Vainu telescope in Kavalur, which is not far from Bangalore. And it's operated by the Indian Institute of Astrophysics. It is it's on a horseshoe mount. The 2.34 meter mirror is sitting here in this chamber, and it can be pointed to any part of the sky by rotating it on this axis as well as on this axis. And this axis is supported on one end by this horseshoe shape cradle, which allows uniquely this telescope to point even at the North Pole, which is not always very feasible in other telescopes of the equatorial mount kind. So this telescope has one drawback in that it is sitting in a region where there is a lot of cloud cover, and very frequently the sky is bad. But along with this telescope and other telescopes on the campus, they have a formidable set of observing equipment at a short distance from Bangalore. And a lot of very interesting results have come out from here. I don't have time to go into results simply because we were to talk about telescopes here. We can discuss results. If people are interested, you can drop me a line or something and we'll discuss it further. Give you another example. I then went all the way from next to Bangalore to the other extreme and went to Hanle in the Ladakh region, where they set up the 2 meter Himalayan Chandra telescope. There's also a wonderful telescope, and it's completely remotely controlled from Bangalore. You do have local people who are on the site to make sure that things are running properly. And it has a whole suite of instruments ranging from images to spectrographs, both optical and in the infrared window. Several instruments are mounted at a time on the telescope, and one can select them through software at short notice. Okay. Now, there is another very interesting telescope which has been built. It is the largest telescope in India at optical wavelengths, in fact. And this is the 4 meter International Liquid Mirror Telescope. So the concept is quite interesting. You have a single mirror, which is made up of accurate surface, but then it has, instead of glass, it has mercury sitting at the center. And when the mirror is rotating at reasonable speed, the mercury spreads across, providing you with a very accurate surface definition, which allows you to build a 4 meter mirror at the fraction of a cost of what a real 4 meter telescope would cost. And the only problem with this kind of a telescope is that you have to point at only the vertical sky, and whatever sky is passing overhead, you can observe it. Okay, so the telescope has several filters, and it's possible to take images in a continuous span. As the sky rotates overhead, the telescope reads out the images, and then it is stored as long strips. I'll show you one example of, so this is the observatory from outside. You have the control room here and then the compressor room and other auxiliary building. Because mercury is a poisonous thing, you're not allowed to go in once it is in operation. And in fact, even during operation, when it is not in operation, only authorized people are allowed access, only those who really need to be in the building. So example of an image from this telescope is this image which I took from the IIRS website. These are among the first images from the ILMT obtained in October 22. And it shows, in fact, one of the asteroids as it was tracked across the field of view of the instrument. The blue track here is from a space debris which is much nearer to us, and because of that made a continuous track in one of the images of this false color composite constituted from multiple images at different bands at different wavelengths in different days. Okay, so that is how the asteroid looks different color on different days, and it shows over here. So these were done at in 3 different bands and then color composited as a false color to bring it out. So the asteroid itself does not move as much, but if you were to combine it as a single long exposure, you would get a trail similar to what this near Earth object has shown on this space debris, which probably was within the Earth-Moon system, maybe somewhere nearby, near Earth satellite, maybe. And that's how it has moved across the entire field in a single exposure. So now I come to the observatories operated by PRL, and I'll conclude very quickly. We're running short of time probably. This is the 1.2 meter, one of the oldest infrared telescopes in India. And we have also here the 43 centimeter telescope inside this small dome, and a 50 centimeter telescope on this peak here, which is just a little small walk from the base to the top. And then now we have the 2.5 meter telescope, which is the largest telescope in this part of the country. It's installed recently and started producing some interesting, very exciting science results. And I'll just show you one. Let me show you photos of each of the telescopes. So this is what the telescope looks like from inside this dome. The dome itself is painted dark black, dark color in the inside, so that it won't reflect any unnecessary light from scattered light from outside. You have the telescope mounted in an equatorial mount, fork mount. So, and here we have the instrument at the focal plane of the telescope. This is the primary mirror. You have a second mirror here called the secondary, and then the light from the primary is reflected by the secondary through a hole in the primary to the focal plane instruments. The focal plane instruments can be changed, and we can have a suite of instruments. Many of them were built in-house at PRL, including several polarimeters and infrared cameras and spectrographs. So this is the first one in the country, and recently we have installed a second one, which is in operation. And new instruments are always being defined and built for this telescope by people at PRL. On the 2.5 meter also we have spectrographs built at PRL. In fact, I should have mentioned that on the 1.2 meter we have a very high resolution spectrograph called PARAS, which discovered the first exoplanet seen from Indian soil. And similarly with the 2.5 meter also we have a high resolution optical spectrograph, which provides very interesting results already. So this is the 2.5 meter telescope, and at the focal plane we have a possibility of mounting 3 instruments, one on the main port and 2 on 2 side ports. We have the 50 centimeter in this kind of a dome here at the top of the peak, and this is what the view looks like from standing from outside and through a kind of transparent dome idea. It's a trick photograph actually. And then this 2.5 already shown you. This is a 43 centimeter in a fully collapsible dome. And the advantage of this is that this kind of a setup is that you can quickly move to any part of the sky in order to look at transient objects at short notice. Okay, so you're not limited by the time that the dome takes to rotate in front of the telescope. The telescope itself can move to any part of the sky in very short notice. We also have an all-sky camera at Mount Abu, and you can see the night sky very nicely. In fact, even the Milky Way at times. But it's also good for fireballs and meteor imaging. And one example is this spectacular image of fireball as it entered the Earth's atmosphere one early morning. This was just before sunrise, well before sunrise, of course, around 4 in the morning, I think. And the entire control room, I was there at the observatory at that time, and then the entire room was filled up with a kind of green light. And when we looked at the image in the all-skies camera, we were able to see this light. It was a very exciting time to be at the control room at that time. So what are the different requirements for solar system science? Because, telescopes wise, the same telescopes that we use for the rest of astronomy, we can make use of for solar system objects also. The main thing is to do with tracking. Okay, solar system objects are nearer to us, and just that's the way you see the nearer trees when you're moving in a train. You see the nearer trees moving faster than the background trees, which appear almost stationary. So the same thing happens here. You see a parallax, and you see the foreground solar system objects moving across the field of view very fast, okay, relatively. So then what we need to do is we need to track the object using what we call non-sidereal rate tracking, which means that you are using tracking rates which are as per the object, not as per the stars. Normally, if you were to take images of the stars, you would then be compensating for the rotation of the Earth's axis. Now, on top of that, you need to also, I hope that you can see this video. It is supposed to show a bright spot at this location, which is the asteroid. It's a near-Earth asteroid called 2004 BL86, which we observed as it flew past very close to the Earth, just 2 times or 3 times the Earth-Moon distance. So it came extremely close to the Earth. Normally, it's just a few hundred meters across and extremely faint. But on this particular night, it brightened up to be one of the brightest of asteroids visible in the night sky. And all these objects which you see passing it are the nearby stars, are the background stars. And the telescope had to really race across the sky to track this asteroid as it moved several degrees in an hour. So the instruments which are at the focus of the telescope decide what kind of science that you would like to do. So we are deciding the instruments based on what are our scientific aims. So we go with spectroscopy, imaging, and polarimetry. I will just briefly tell you something about spectroscopy because that's something of interest, I think, for many people. This is one of the instruments on the 50 centimeter as well as it has been used on the 1.2 meter. This is showing it on the 50 centimeter. This is on the 1.2 meter. And it has a spectral resolution of 1000 with a wavelength coverage from 380 to 780 nanometers. And this is what the instrument looks like mounted on the 1.2 meter. So this mirror is 1.2 meters across. So the optical path looks like this. At the focal plane of the telescope, you have a slit, and the light that you don't want to pass through to the slit is reflected to another mirror here and passed into what we call the guiding camera, that is this blue camera. And the red one goes through the spectrograph, gets reflected from this mirror, goes through a collimator lens, is incident on the grating as a parallel beam, then passes through another focusing objective lens, and then falls on the spectrograph acquisition CCD or camera, that is this red CCD. So this camera has been used extensively for over 24 comets in the last 6 to 8 years. And this is the advantage that because this has this guiding camera, you can actually see the object as it moves across the field of view. You can, of course, move the telescope to compensate for this movement, but there will always be some minor residual movement, which allows, and this kind of a guide camera allows you to build up the signal. So the guide camera has exposures of 5 to 10 seconds, whereas on the acquisition camera, where you have split the light into a spectrum, you need a exposure of merely 1 hour. Okay, so in order to build up the signal, you need to make sure that you are tracking the comet accurately. So that is done by imaging the camera, the comet as the telescope follows it. Okay, so if needed, then you can make corrections. And this is the kind of spectrum that you can generate from this. I covered this a little briefly, but since there was a question in the previous talk, just to tell you that there are some very specific signatures of different molecular species, and these are pretty unique. And so it is relatively easy to distinguish at a coarse level what are the kind of molecules present in the coma of the comet. We'll go into more details if someone has an interest. So summary is that, telescopes are rarely used by astronomers to see the objects by eye. So this is something which people see in the movies, and also, of course, you have heard about how Galileo discovered the moons of Jupiter by looking at Jupiter through his self-made telescope. But nowadays, we rarely do that. We actually build instruments and put them on the focal plane of the telescope. And the telescope has the only job of collecting light from the distant heavenly bodies and putting it into our instruments. So I think I'll stop with that and take questions.
Thank you, sir, for an insightful lecture on the use of telescopes for studying the solar system bodies and covering all the basic things regarding what all telescopes are there, what are they used for, and all these things. I hope there will be good amount of questions waiting for you in this relation. So there is one question which says, how can we detect the uninterrupted signals from the space, because we have so many electronic instruments on Earth? Is it interfering with them? Okay,
that's a very nice question, in fact. And if you go towards, for example, this is a matter of big concern, especially at radio wavelengths. Okay, and in fact, we had at PRL we had a radio antenna which was working in the same frequency range where the FM stations have come up. Okay, so 100 megahertz, roughly 105 megahertz. We had a radio antenna. Of course, we stopped using it, and so then it was allowed for other uses. But normally, what is happening is that typically you can sense the signals from mobile phones to even various other kind of electronic gadgets, where the radio telescopes are very sensitive to this kind of interference. In fact, there are a class of objects which were seen only with one specific telescope, okay, in Australia. And people were trying to target this and trying to see if they could match it at other radio telescopes, and found that it was not at all possible. Eventually, it was traced to a microwave cooker. Okay, so it was a microwave stove in the kitchen of the observatory, which people used to use periodically. So that was giving rise to periodic signals in the radio telescope. And people were wondering from where this kind of signal is coming. Okay, so that's the kind of issue that can happen. At optical wavelengths, we have little less interference from this kind of radio waves, but we do have optical light pollution of our own to worry about. And now, of course, you have the whole area of space satellites, which create trails across the sensors whenever we are observing for long exposures. So, yeah, so I hope that answers his question.
Yes, thank you. And the next question would be, can you briefly explain on the topic of adaptive optics, like how do you detect the wavefront, how is the wavefront sensing for image correction done in a brief manner?
Right. Okay. So the simplest mode is that you take an image of a star, seen by the telescope and split it over using what is called a Hartmann mask, okay, or a Hartmann screen, and it creates images over a large area. And this allows you to measure the wavefront distortions over the field of view. And once you know what kind of distortions you are seeing in different parts of the mirror, you can then compensate for that by moving a third mirror, a flexible mirror. You move it in directions which are designed to compensate for the variations which you are seeing in real time. So this has been done very successfully in very large telescopes, and it is a very effective way of improving the resolution of the telescope, okay, beyond what the twinkling would otherwise allow.
Okay, and the next question would be the basic difference between a radio telescope and optical telescope. Why are radio telescopes arrays while optical telescopes are mirrors?
Okay, that's a very nice question. In fact, I must compliment whoever asked this. And it also answers why you need so many numbers of arrays. Okay, so the whole idea is that it has to come down to the basic principles of optics. The larger your collecting area, the diameter of the collecting area, better is your spatial resolution. Okay, that is why we go for larger and larger mirrors. Apart from collecting more number of photons, you are also wanting to collect, you improve your spatial resolution. Now at radio wavelengths are already large, right? So lambda by d means is essentially proportional to the spatial resolution. So d being large, lambda being large, d has to be also large. Okay, so in terms of at radio wavelengths or radio frequencies, the telescope would have to be several kilometers across. Now it's not possible to have a single dish which is of that size and to make it steerable. So what people have found is that there is a possibility of doing it in interferometric space, so in frequency domain rather than in spatial domain. So what we do is we have antenna irregularly spread all over a circle with large number of antenna close to the center, and then you have in the case of GMRT, for example, you have a Y-shape layout, and this allows to synthesize a large single dish kind of effect as you combine the data from all these different antennae. And the same concept has also been done at smaller wavelengths. In fact, ALMA is one example, and then people have also tried this at infrared and optical, and with kind of mixed success, I would say. Although at infrared, it's relatively much easier than in the optical domain. Main thing being that you need to time the received photons in a very nice, in a very accurate way. Okay.
Okay, and you had talked about space telescopes, various space telescopes, and there is a question regarding the same. How do these telescopes tackle the very harsh conditions in space, the space weather conditions? How do they tackle these telescopes?
Correct. Yeah. Again, another nice question. So typically, what happens is that the optics itself is space hardened, and the electronics also, but the detectors detect whatever energy comes through into the field of view. So for example, in case of infrared space observatory or any of these observatories, the final images that you see are extremely pretty and nice, but then if you were to look at the raw images, it would be hard to believe that really there's a lot of signal in there. And the reason is because there's a lot of cosmic rays and other photons, stray photons, which are roaming around in the in space, and which hit the detector whether they are through the optics or not. So they end up leaving tracks in the detector. Now what is done is that you take multiple images and then you combine. So whatever random characters are there or cosmic rays are there, they will be only in one image, and then you can drop that part of the data and then combine with the other data frames. So that is the way we go from the hundreds of raw images to finally reach one colorful image.
And the last two questions are a bit in a general sense. Anyone would have these in mind, like, can Pluto be seen from any telescope? Is it visible similar to Jupiter or
Okay. Yeah, in fact, Pluto is a very tiny object. It's hardly in any way differentiable from a star. It's just a point source as far as Earth-based telescopes are concerned, and especially if you were to look through the telescope. I have actually looked at Pluto once during a session when we were introducing our junior research fellows to general astronomy. At that time, we had put the eyepiece at the telescope. It's a very rare opportunity. And usually we see only Jupiter and Saturn and maybe the moon, but these were very bright. And so we went and looked at the other objects. Uranus appears as a kind of blue disk, but Pluto appears just like any other stellar object there. So unless you don't have the coordinates, you won't know that it is Pluto if you were to look at it as a passing glance. Okay, it's only when you give long exposure and track that you see that it is long.
And the last question would be, that is a very general question which anyone attending this lecture would be having in mind, and you are the best person who can answer that. Are there any affordable telescopes for purchasing?
Okay, so I think the best answer to that is, it is not so difficult to make your own telescope. You can, at a pinch, you can start with optics from your friendly spectacle maker. You just go and ask him for a lens which is of, let's say, plus 0.5 power, and then you buy an eyepiece and just put them in a tube. So this plus 0.5 power means it's 1 meter focal length, okay? And you want a long focal length so that you will minimize the amount of aberrations. And you put a normal microscope eyepiece or any reasonable eyepiece. Eyepieces are essentially two convex lenses which are, again, they are relatively high power lenses. So you can, in fact, try combining maybe plus 6 or plus 5 power lenses. And you can build your telescope that way. In fact, that kind of a telescope is good enough to show you craters on the moon. And if the sky is steady, then you can even see the rings of Saturn. I would recommend anybody to try that. I mean, the cost is less than 2,000 rupees, so it's worth doing.
Okay, there is just one last question. I missed it out. You had shown an image of ALMA telescope.
Right.
This participant wants to know, why was the sky so dark? Is it because of the lesser dense atmosphere at that height, or was it the camera exposure, or was it dawn time, or something like that?
Okay. Let me just recall.
ALMA.
This one, yes. Oh, yes, okay. So in fact, as you go to higher altitudes, the amount of dust particles in the Earth's atmosphere reduces, and all the pollution reduces. So essentially, you end up having a good scattering only in the blue, and then all the white which comes from the dust goes away. So the sky appears blue. In fact, you can see sometimes this kind of blue skies even at lower altitudes, like in Mount Abu, when you're just above the boundary layer. Okay. Something. So it's because of that.
So that is all for now. I once again thank you for this insightful lecture and patiently answering all the questions. I now hand over the session to Mr. Praveen Kumar. Thank you for having me.
Sure.
Thank you very much, Professor Shashikiran Ganesh, for a wonderful lecture on these telescopes for solar system studies. And also, I would like to thank Dr. Aravind for moderating this session. Thank you, both of you. And to the participants, we will be meeting again tomorrow at 3:30. So please be tuned on that.